going to take the portion of blackbody radiation once more, especially the derivation part. A blackbody is an idealized concept. It's a surface which absorbs all the radiations that falls on it. Why do we take such a concept? Is because we want to study the thermal radiations. That is, when a body is heated, it emits radiation. That is called thermal radiation. And the radiation depends, nature of radiation depends on the temperature. We don't want that to be influenced by the nature of the surface of the body as well. Usually, if we want to study the variation of one parameter as a function of another parameter, all the rest of parameters should be constant. To get that here, we take the case of blackbody radiation, in whose case, when it is heated, the radiation that is emitted will be independent of the nature of the body. So we take such an idealized blackbody radiation. It is often achieved by making a cavity with a small hole, and the inner walls of the cavity are painted black. And so now it is heated. So through this hole, the thermal radiations will come out. As temperature varies, the nature of the radiation will also vary. If we want to study the variation of the nature of the emission, we should study what is the intensity of radiation in different wavelength or frequency ranges. For that, we make the upcoming radiation out of a blackbody, we make it incident on a prism. A prism will split in the individual components of the radiation into different angles. Then, if we keep a detector at these different angles, we will get the intensity of radiation, emitted radiation in different wavelengths. Then, we can plot that as a function of wavelength or frequency. That is blackbody radiation. We don't plot intensity as such. Usually we plot energy density. That is energy that is emitted per unit volume. So we measure the volume of the cavity and the total energy emitted we calculate and divide it by volume, you get energy density U. It can be expressed either in terms of frequency or wavelength. So this is the type of curve that we get in blackbody radiation. So this is energy density and this is wavelength. So this is the experiment curve that we got. But to explain what is happening, different physicists put forward different theories for blackbody radiation. And then we'll be seeing whether that mathematical equation gives a curve like this. So the first two scientists who explained it was Rayleigh-Jeans. Rayleigh considered that the radiations, thermal radiations inside the cavity will go and get reflected from the walls and then it will make standing waves. So different modes of vibration. Then we can calculate how many modes will be there inside the cavity totally between a wavelength range lambda and lambda plus d lambda, number of modes. And then we multiply that by average energy per mode. That will give you the total energy. Number of modes into average energy of each mode. That will give you total energy. So first we have to calculate the number of modes. That is the classical concept. But the curve that they obtained thus failed because it had a lambda raised to 4 in the denominator. So as wavelength increases, the energy density went to infinity. That is called ultraviolet catastrophe. When lambda decreases or frequency increases, it went to infinity. So that was a failure. So Planck put forward another theory where he treated the thermal radiation as not as waves but as particles, quanta of energy, and he proposed each quanta have energy h nu, and then average energy, he calculated an expression for the average energy per quanta and multiplied these two and got an expression for energy, and that perfectly fitted this. So essentially in both cases, classical and the other cases, what they do is the number of modes or number of quanta into average energy per mode or average energy per quanta. So let us take the classical case. So we have to calculate how many number of modes are there inside the cavity. Suppose this is a cubical cavity and it has a side L. So let us calculate what will be the boundary conditions for this. Wait a minute. The boundary conditions, you know that nodes should be there on the walls. So N lambda by 2 equal to N. Here that N. So here N equal to 2N by lambda. But we know that C equal to mu lambda. So 1 by lambda is mu by C. So here is 2N mu by C. This is N. This will be quantized in 3 directions, Nx, Ny, Nz. And one set of Nx, Ny, Nz will correspond to one mode. So we have to find how many such sets will be there, points will be there. This can be done by imagining n strings, and then you will get here nx square plus ny square plus nz square equal to 4n square mu square by c square. This is an expression for a sphere. X square plus y square plus x square equal to r square. So this is the square root of this is the radius of that sphere. In the nx, ny, nz space. So how many points are there inside this? say how many number of modes are there. But we can calculate only the positive quadrant. So it will be, the total volume will be 1 by 8 into 4 pi by 3 r cube. Where r will be square root this. So the radius will be this. So the total number of modes in the positive quadrant will be 1 by 8 into 4 pi by 3 r cube 2n mu by c by cube. So that this 8 and this 8 get cancelled. 4 pi by 3 l cube mu cube by c cube. This l cube is volume. So this tells me the number of modes. Now we have to calculate what is the number of modes, not the whole number of modes from 0 to mu. That is this. But what we want is between mu and mu into delta, mu plus d mu. That range. That range, what will be the number of modes? So if this is n, the dn will be 4 pi d by 3. Differentiate this. 3 mu square by c cube. So we get 4 pi d mu square by c cube. This is the number of modes between mu and mu plus d mu. Okay. Inside the whole cavity. Now, if we calculate, we have to convert it into wavelength. That is the doubt one student had. All the expressions that we get in terms of mu, how to convert it into terms of lambda. Number of modes in the range mu between 4 pi d, there is also d, 4 pi d by c cube mu square d. Whenever we have to convert from mu to lambda, we use the expression c equal to mu lambda. So mu equal to c by lambda. d mu will be 1 by lambda differential. C by lambda square d lambda. Minus c is there, but it doesn't matter since we are counting the number. So here, number of modes in the range interval d lambda will be 4 pi d by c cube. Mu square, c square by lambda square, d mu is c by lambda square d lambda. So it will be c cube get cancelled. 4 pi d by lambda raised to 4 d lambda. But there are two modes of vibration, because if the wave is moving in this direction, transverse waves will be there in this direction as well as in this direction. So, this is the number of modes for one polarization. There will be two such polarizations. So, since two polarizations, number of modes will be this into 8. So, this is the number of waves, modes in the lambda. Similarly, number of modes in frequency d will be 8 pi by d c cube mu square. These are the expressions. Now, this many modes will be there. classical equipartition theory, each mode will have average energy kT. Equipartition theory assigns 1 by 2 kT for each type of energy or degree of freedom. Here it's fine, there will be potential energy as well as kinetic energy, and it will be kT. Average energy per mode is kT. So, total energy in the range, in the interval d nu dt, this into 8 pi d by lambda raised to 4 into kT d lambda, or 8 pi d by c cube square kT d nu. Now, if we want energy density, then this divided by energy density is total energy per unit volume. So, here there is volume. So, energy density will be u lambda d lambda will be, and u nu d nu will be. So, these are the expressions. And when we plot that, we see that lambda raised to 4 or mu square. Lambda raised to 4 means when wavelength becomes small, this curve will go to infinity. So, this is ultraviolet catastrophe. In the frequency thing, u nu d nu, it will be, as frequency increases, so this is wrong. It doesn't go to infinity. So these expressions are wrong. So enter Planck's. Planck said that the energy is emitted by the walls of the cavity. We can consider the cavity is made up of